Hi. Now let us talk about the method of equilibrium. Okay, in the previous class I have told you how we can use the method of equilibrium or the method of equations to find the stresses on an oblique plane, right? So in this case, I am just going to take an example to illustrate the method of equilibrium. Okay, so this lecture is going to be an example, but most importantly this will be walk-through concept of method of equilibrium, okay, to find the stresses on an oblique plane, or to find the to carry out the plane stress transformation. Okay, now here we have this point, and we have these stresses. We have the normal stress here 65 megapascal, and this is a shear stress and it is 20 megapascal, as you can see here. Okay, now we have this AB. Okay, it is inclined at an angle of 30 degrees. Okay, so in the method of equilibrium, when we want to find the plane stress condition on the what we do, we first of all draw the we draw the coordinate system. Okay, I am going to show you an easy method and also this way you will do less mistakes. Okay, so always remember like this. Okay, so this is our coordinate system. Okay, so this is our original coordinate system. Okay, so this is the coordinate system for this point. Okay, so this 20 megapascal, 65 megapascal is corresponding to this xy coordinate system. Okay, now it is showing this plane has rotated by an angle of 30 degrees. Okay, so it is something like this, right? Like this, right? So this plane is rotated clockwise by 30 degrees, right? So we will rotate the we are going to rotate this coordinate system. Okay, then we will find the stresses on this. Okay, so let me draw another coordinate system. Like this. Okay, now we are going to rotate it exactly the same as this plane. Okay, so it is clockwise 30 degrees, so we are going to rotate this clockwise 30 degrees. Okay, so this is like this. Yes, so this x has reached to this, right? It is 30 degrees, right? So this was x. Now the rotate, when it is rotated, it becomes x prime, right? Similarly, this reaches to this by 30 degrees, right? Similarly, this will shift to the red. The green is the old coordinates axis, right, and the red is the new coordinate axis. Okay, so this red one is the the new position of this one. Okay, so that's why I'm showing you the arrow. Okay, so it will, of course, it will also rotate by 30 degrees, and this will also rotate by 30 degrees. Okay, so this is how we do in method of equilibrium. Okay, the reason I took the example, because I wanted to explain you live. Okay, because this is more kind of procedure. Okay, so now we have drawn the now this was y axis, right, positive y axis, and this is the rotated, so it is y prime, right, this one. Okay, now what we have to do, we have to find the stresses on this oblique plane AB. Okay, so I am going to draw this triangle. Okay, here something like this. Okay, excuse my handwriting. Now this is 30 degrees, right? Okay, now I will assume, let us say the area here is delta A. Okay, so this oblique plane has an area of delta A, but the area is perpendicular to this plane. Okay, you will not see this. Okay, so it is perpendicular to this paper. Okay, so if it is delta A, so when we find the components of delta A, so this is going to be delta A cosine of 30 degrees, right, and this one is going to be del A sine of 30 degrees, right? So again I will draw another triangle. Okay, but this time I will keep the space around. Okay, I will draw the triangle here, okay. So this one is our triangle, okay. Now I will draw the stresses, okay. I will draw the force, then I will write down the equation of for the forces. So I will this on this triangle I will show this is the same triangle, okay. I am drawing it here. By the way, this is AB, okay. So this is the AB line, okay. Now what are the different stresses? Now you can see here on this side we have a stress of 65 megapascal normal, and we have a shear stress of, what is the value of this shear stress? It is 20, okay. So 20 means it is for all the shear stresses, okay. So here we have 20 megapascal, but we will not show the stress, we will show the area, okay. So we will show the force, okay. So what is force? Force is stress multiplied by area, okay, because stress is force divided by time, force divided by area, right? So whatever the stress is on this, right, so the area here is delta A cosine of 30 degrees, okay. So if I want to show the force here, because of this 65, because 65 is acting here, okay, so it is going to be 65 times delta A cosine of 30 degrees, okay, because here the area is cosine of 30 degrees, okay. Now from this side, if you see on this side, this is 20 megapascal. So what is the force equivalent of this stress, 20 megapascal stress? It is 20 times, it is acting on this side, right? So the area here is 20 times delta A sine 30 degrees, okay. So now let's do it, okay. So this is 65, okay, and here the area is delta A cosine of 30 degrees. So this one is going to be 65 times delta A cosine of 30 degree, okay. So this is the force component due to this 65 megapascal normal stress, okay. Then we have the shear stress here, okay. Shear stress I will draw a bit far. Why I keep the lot of space? Because we have to draw the components, okay. We will resolve this along this perpendicular to this AB and along the AB, okay. So I will explain everything, just keep some space in between, okay, and you will understand everything as we move on. So this one is what is it? It is 20, okay, and what is the area? Area is this, right? 20 times delta A cosine of 30 degrees, okay. Now this one is delta A sine 30. So this is 20 times what? 20 times delta A sine 30, right? Sine of 30 degrees, okay. So we only have the shear stress, we don't have any normal stress on this, okay. So we draw the stresses on the two sides of the triangle. Now this side of the triangle we have to find the stress, okay. So what we have to find? We have to find the stress is going to be this, like this, right? Sigma normal stress is going to be along y dash, right? Y dash, and the shear stress is going to be along x dash, okay. So it is going to be something like this, okay. So if I draw exactly the same axis here, okay, so it is going to be sigma x dash times delta A, right? Why? Because here the area is delta A, okay, and sigma, this is sigma y dash, not x dash, okay, sigma y dash, and then we have shear is going to be along the x dash, okay. So here it is going to be shear stress, we denote it with tau x prime y prime times delta A, okay, because stress multiplied by area is force, okay. Now I will show you why I show it like this, because this is what we want to find, okay, because we want to find the stress. This delta A 20, I forgot to write delta A here, okay, it was delta A sine 30, right? So it is delta A sine 30 degrees, okay. So why I write like this? Because it is showing you, because we have to find what is the what is the whole purpose of method of equilibrium. We want to find the normal stress on the oblique plane AB, right? Because it is the oblique plane, it is rotated, so we denote it with what? prime, right? So this shows us the normal component of this y dash. This is the normal component on oblique, and we also want to find the shear stress on the oblique plane, and this x prime shows, because you can see, you can understand this is along the plane AB, right? As you can understand from the sense, okay. And this y dash, you can see, you can understand it is perpendicular to the AB, okay. So this is the reason, because it is the y dash, so I will write sigma y prime, right? Sigma y prime, and here I will write tau x y, but all prime, okay. So this is the reason I did it like this, okay. So this is the reason I did it like this, okay. Now we will, what we do now, next we will find the components. I mean, we will only draw the components, okay. So we will find two components of all of them. First is along the oblique plane, so that when we apply the equation of equilibrium along the oblique plane, tau x dash x prime y prime, okay, then tau x prime y x prime will include the because this is along the oblique plane, so along the oblique plane components will be included when we apply the equilibrium equation along this. And when we apply the equation of equilibrium normal to the oblique plane, so all the normal components, okay, normal to this oblique plane, they will be included in that equation, okay. So let us find the component of each force, okay, along the oblique plane and normal to the oblique plane, okay. I hope this makes sense. Now why I draw this, it will help you a lot, okay. This is just a this is a very fast guide, okay. So if I write it here, okay, this is it is going to help you a lot, okay. So I will show you why. Now let us find the components of this one, okay. I will choose this color. Now let us find the components of this 20 delta A cosine of 30 degrees along the along the oblique plane and perpendicular to the oblique plane, okay. Now this is, you can see, this is like it is like this component, right, like this one, okay. So it is going to be, normal is going to be like this, okay, this is the normal, and the along is going to be like here, okay, along is going to be here, okay, and here it is making an angle of 30 degrees, okay, 30 degrees. So the reason I draw this, because you have to understood where this arrow is, okay. It is like here, okay, because this is the horizontal, so this is also horizontal, okay. So one component will be here and another component will be here, okay. This component is normal, as you can see, this is normal, right, this one is normal, and this one is along AB, okay, this one is along AB, okay. So this is the reason I show it like, this is the reason I recommend you this diagram. This is very important, okay. Now we draw the components of this, okay. Now let us find the components of this 65 along parallel and perpendicular. Now perpendicular is this, okay, perpendicular to this, and along is this, right, along is this, right. Now what is the angle? Now you can see it is, this one is here, right, it is here, and this is the angle 30 degrees, okay, 30 degrees, right. Now let us move on to this one, okay. Now it is acting downwards, okay. So along it is going to be, perpendicular is this, and along it is going to be this, right. Now this is perpendicular, and this is making along perpendicular, this is making an angle of 30 degrees, okay. So this is 30 degrees, okay. I hope you are understanding, okay. If you have any doubts, you can comment, okay. I am trying my best, I really trying my best to explain. And again, I am saying this diagram is really very, very important. It will help you, okay. So you should always draw this first, okay. Now we don't have to find the components of this one, oblique plane, normal stress and shear stress, because they are, one is perpendicular, already perpendicular to the oblique plane AB, and another is along the oblique plane AB. Okay, so these are already along our desired direction, so we don't have to find components in this. Okay, now because why it is called method of equilibrium, now because we will apply the equations of equilibrium. Okay, we will apply equations we are going to apply equations of equilibrium. Okay, so let us apply. So let us apply the first equation along the perpendicular to the oblique plane. So this is along the y-axis, right, y dash. So summation of forces along the y dash is 0, right. This is the equation of equilibrium along the normal to oblique plane. Okay, so oblique plane is in this direction. Okay, in this direction, so I will keep this direction as positive, and whatever is opposite to this, for example like this, it is going to be negative because it is opposite to this. Okay, so let us apply this. Now sigma y delta A, right, this one. Now let us see the component, normal component of this force. What is the normal component? This is the normal component. Okay, and it is opposite to this, so it is going to be negative 20 delta A sine 30, delta A sine 30, and the normal is making an angle of 30 degrees, right. So it is cosine of 30, right, cos of 30 degrees. Okay, so remember to apply this cosine to, if it will have 1, this sine 30 degree, it is because of what? It is because of the area. Remember, delta A sine 30 degrees. So delta A cos 30, delta A sine 30, these are the components of the area. Okay, so the first trigonometric function, okay, this is the because of the area, and the second is because of the orientation, okay, of the force. Okay, so we have applied this. Now let us apply the component of this one, but normal. Okay, so first of all let's write the force. So you can see the force is along, right, this is the normal component, right, and it is along this, so it is plus 65 delta A cosine of 30 degrees. Now it is this original, right, because the component is this one, right, and it is making an angle of 30 degrees, so it is cosine of 30 degrees. Okay, now we applied the normal component here. Okay, now let us write the normal component of this one, right. So it is, you can see this one is the normal component, right, and it is opposite to this. Okay, so it is 20 delta A, so it is going to be negative 20 delta A cosine of 30 degrees, right. Now it is making an angle of 30 degrees with this one, with the horizontal one, I mean along, this is one is along, right, but we won't find this one, right. So it is sine of 30 degrees, right, not cosine. Cosine will be the along the oblique plane, right. So sine of 30 degrees. So we have included all the normal components in every force. Okay, so I will equate all of it to 0. Okay, now when we put this, now let me show you something here. This delta A, this delta A, this delta A, this delta A, so all the delta A's will cancel out. Okay, so when we put this in calculator, we will get the value of sigma y. Okay, so before finding this, let me apply the another equation. Okay, so I will apply the summation of force along this x-axis. Okay, let me show you why it is x-axis. You can see it is here. This is x-axis, right, this is x-axis here, right, this is x-axis, x prime axis, and this one was y prime, right, this one was y prime axis. Okay, so we applied the equilibrium equation along y-axis, so let us apply now equilibrium equation along the axis, x prime axis. Okay, so summation of forces along x prime axis is 0. Okay, so it is something like this, right, something like this, it is positive. Okay, so whatever is in this direction, okay, or in this direction is positive, and if something is opposite, for example like this, it is opposite to this. Okay, so that is going to be negative. Okay, so first let's write this one, tau x prime y prime delta a. So we wrote this one. Then now let us write the parallel component of this force. Okay, so it is, you can see the direction is same, right? So it is, we are going to use positive here. Okay, so plus 20 delta a sine 30 degrees. Okay, but it is making an angle of this one, right? The angle is here, but we want to find this one, so it is going to be sine of 30 degrees. Okay, so cosine was this one, and the sine is going to be this one. Okay, so it is going to be sine of 30 degrees. Okay, so we have included this one. Now let us apply this one. Now you can see this is opposite to this arrow, right? This component, so it is negative minus 65 delta a cosine of 30, and that is going to be sine 30, right? Sine 30s. Then what we have, again we have this one, it is opposite, right? It is like this, and but it is like this, right? So it is going to be negative 20 delta a cos 30 times cos 30, right? Negative 20 delta a cos 30 times cos 30 degrees is equal to 0. Okay, so it is going to give me the tau x prime y prime. Okay, so let me use the calculator to find these values. Again, these delta a's will cancel out. Okay, so let us first solve this equation. Okay, I will denote the sigma x sigma y with x. Okay, I got the value of sigma y to be minus 31.43. now the unit is what? They are all in megapascal. Okay, so it is also going to be in megapascal. Okay, now what is negative? Negative means our actual direction is opposite to what we assume. So here we assume the normal stress is like this, but actual is like this. Okay, and the value of it is what? 31.43 megapascal. Okay, so I would rather write it, I will do the correction later on. Okay, so let me apply the another equation. I got 38.146 megapascal. Okay, and I have verified these answers. Okay, and they are perfectly correct. Okay, so if I draw these oblique plane here, this oblique plane. Okay, okay, so I will show you here. So what we have sigma y is minus 31.43. it means like this, right? Minus 31.43, right? So it is like this, 31.43 megapascal is the normal stress on this oblique plane, right? And shear stress is along this, it is 38.146. Okay, and the shear stress is 38.146 megapascal. Okay, so we got the state of stress on the AB plane. Okay, so this is how we apply the the method of equilibrium. Okay, I hope you got the idea now. Okay, so again I am telling you, this is a lot important. Okay, it will help you. It is very easy to draw, and it will tell you very easy which angle is what. Okay, 30 degrees. Okay, so I was I can draw these 30-degree angles, all of these I can do it without this too. Okay, but I would need to use my mind and to guess. So this one is very easy, so I will keep this blue vector, I will assume it is this. So this one is 30, very fast, right? So you can find these angles with the help of this. Okay, very fast. Okay, so this is the method of equilibrium. Okay, now in the next class we will talk about the equation method in the plane stress transformation. Okay, so that's it for this class. Okay, now if you have any doubts, you can comment or you can contact me. Okay, and that's it for this class. See you in the next class. Thank you.